problem solving uniform motion. Okay, so our objective, we want to solve uniform motion problems. Okay, let's define a bit about what that means to be a uniform motion problem. So uniform motion means that objects are moving at a constant or a uniform speed. In other words, the speed does not vary. Okay, so it's required, your speed can't be changing in these kind of problems. We're going to assume that your speed is always consistent. And the formula for these things is the distance is equal to the rate times the time. Okay, so the distance is how far you go, the distance that you cover. The rate is your average speed, miles per hour, for example, feet per second, for example. And the time, of course, is just a time. All right, and some notes to remember are some notes that'll be useful for these problems. To say that distance equals rate times time is equivalent to saying that rate equals the distance divided by the time. If I go up here and I divide both sides by t, rate is equal to the distance divided by the time. It's also equivalent to saying that the time is equal to the distance divided by the rate. So these three formulas are equivalent, and you may find yourself, as you're working these problems, finding another version to be more helpful as you look to set up your equation. The second point to remember with these problems is that your units must be consistent. Okay, so for example, if your rate is in miles per hour, then your distance must be in miles and your time must be in hours. So your units have to remain consistent. And the third thing to point out, the third note for these kind of problems is seriously consider organizing yourself with a table. And the table would look similar to this one, where you're going to have two situations, you're going to have two people traveling, two objects traveling, two directions perhaps. And so each of those has a line, and then each of those is going to have a distance, a rate, and a time. Now, they may be equal sometimes, but for each of these, for situation, person, object 1, you want to organize that distance, that rate, and that time. And for situation, person, object, etc., 2, you want to organize its or that person's distance, rate, and time. Okay, I'm gonna do 3 examples here. They're all a little bit different. Before we do that, though, let's remember, and I'll just put this up here briefly. This is the problem-solving format that we've been working with. Okay, so step 1, reading carefully, noting exactly what you're looking for, identifying relevant formulas you may need, and maybe thinking about realistic possibilities for the answer. In step 2, can you draw a picture that will help you? In step 3, assign a letter or variable to represent what you're looking for, and as best you can, minimize the number of letters, because as we know, one letter or one variable can be solved with one equation, but as soon as you go to 2, you need 2 equations, and as soon as you go to 3, you need 3 equations. Step 4, I talked about in the previous video lecture, is probably the most difficult. List all your facts. We got to translate those into mathematical expressions, and we need to come up with an equation. And again, here's where we're going to spend a lot of time with the chart, the table we just talked about. Step 5, once you've got the equation, solve it. That's usually a pretty simple part. And then step 6, check your solution with the facts in the problem to make sure that it agrees. So if you need to pause this to read over that and make sure that's good, that's fine. I'm going to continue. Okay, example number 1. In the distance, rate, in uniform motion problems. Okay, so a car is leaving San Francisco. It's traveling toward Los Angeles at a speed of 60 miles per hour. Okay, At the same time, a professional cyclist is leaving Los Angeles and traveling toward San Francisco at a speed of 20 miles per hour. Okay? If Los Angeles and San Francisco are 400 miles apart, how many hours will it take them to meet? Okay? So let's go through. Step 1. Whoops, I want to put a 1 there. Okay? Let's talk about what are we looking for? Okay? We're looking for number of hours it will take them to meet. Notice I have the units in here. Okay, I didn't just say time it will take them to meet. This question is looking for hours, and I want to make sure I'm focused on that for my units. Okay, what else do we want to? We want to identify formulas. Well, this is a uniform motion problem. We're going at 60 miles per hour for the car. The cyclist at 20 miles per hour. So this is uniform motion. Distance equals rate times time. And let's take a stab at this. What am I going to assume? Well, the car is doing 60 miles per hour, and it's 400 miles from one city to the next. I can just estimate that no matter what, it's going to be less than 10 hours. That's just a really general estimation on this, because 60 miles an hour for 10 hours is going to get the car 600 miles, and we only have to go 400 miles. So I'm just kind of ballparking. My answer better be less than 10. You might can do a little bit better with your mental math. I'm just going to stop it there with that. Step 2, can you draw a picture? Not particularly helpful in distance equal rate times time problems, so I'm going to move on. Move a little bit. Step 3, let's define our unknown. Assign a letter or variable. Assign a letter or variable. Okay, let's have T. T equals number of hours it will take them to meet. I realize I just written the exact same thing and I'm going a bit overboard, but as an instructional video, I want to kind of clearly show the steps. So that's what I'm doing with step 3. That's what I'm looking for. T is my unknown here. Okay, step 4, the most difficult step. We got to organize all this stuff, come up with expressions, and come up with an equation. So what do we know? Okay, let's take a look. In this case, our two things are a car, our two people, our two situations. CYC. We have a car and a cyclist. Okay. Whoops. Okay, we have a car and a cyclist. Don't know how far I got to draw. We'll see how it turns out. And we know for each of them, they're each traveling a distance. They each have their own rate. And they each have a time. So these are my two situations, or my two people, or how I'd like to define it, a car and a cyclist. Okay, T, the number of hours it will take them to meet. Well, they're both going to, if they're going to meet, they're both going to have traveled the same number of hours. So they both get a T here. Now I have the one variable. I want to build the rest of this using the one variable if I can. Okay, let's see here. Rate. Okay, the car is traveling at 60 miles per hour. Well, let's see, our time, of course, is in hours. The car is traveling at 60 miles per hour, and the cyclist is traveling at 20 miles per hour. That's the rate we're given, and we want to make sure we note that our time in hours and our rates time match up. When we know the distance, do we know the distance? Well, we know that distance equals, I don't want to introduce another variable. Distance equals rate times time. So the car's distance is going to be 60 times t, and the cyclist's distance is going to be 20 times t. So I filled out my table using the one variable, the one unknown. Okay, now I got to come up with an equation. So what else do I know? Well, I know the total distance is equal to 400 miles. And of course, my distance here will be in miles. And the 400 miles is equal to the car's distance plus the cyclist's distance. Now I have to kind of work to understand, I have to work kind of a little bit of work to see that. But we know that 400 miles is the total distance, so I got to add up something to get there. And I'm adding up the car's distance and the cyclist's distance. So now I'm in a good place. Okay, this leads me to 400 is equal to the car's distance, which is here. The car's distance is 60t, plus the cyclist's distance. The cyclist's distance is 20t. And I've just finished step 4, the most difficult step. I came up with an equation. Okay, so now step 5. 400 equals 60t plus 22. Let's solve that equation. How about 400 equals 60t? Whoops. We can at least add those up. How about 400 equals 80t? Divide by 80, divide by 80, and t is equal to 5. So t is equal to 5 hours until they meet. Okay, let me come a little bit higher here so we can see my answer. Okay, now let's take a look at step 6. By the way, I remember I had said no matter what, it's going to be fewer than 10 hours, and 5 hours certainly is fewer than 10 hours. So I feel pretty good about my answer. Let's see. Let's just kind of do a check. So in 5 hours, okay, the car travels. Well, the car is traveling at 60 miles per hour. So the car travels 60 times 5. The car travels 300 miles. Okay, let's see here. In 5 hours, the cyclist travels, well, the cyclist is traveling 20 miles an hour. So the cyclist travels 20 times 5, which is 100 miles. Well, that worked. 300 plus 100, there's your total of 400 miles. That's what we're looking for. Okay, let's take a look at a second example. Let me find my paper. Where did I put it? Okay, example 2. We got a community college club. This community college club is traveling by van from Asheville to Chapel Hill and then back. Okay, on the way to Chapel Hill, they averaged 50 miles per hour. On the return trip to Asheville, they averaged 40 miles per hour. If the round trip took 9 hours, how far is it from Asheville to Chapel Hill? Okay, let's figure this out. Okay, so step 1. Okay, what I need to, what am I looking for? Identify clearly. Number of miles between Asheville and Chapel Hill. That's what I'm looking for. Okay, now what else other things I need to identify that are relevant? Well, we know this is a distance equals rate times time problem because I have an average speed. I've got hours in here. We're traveling, so distance equals rate times time. And I don't know. Let's take a ballpark. Round trip took 9 hours. If they averaged 50 miles for the entire 9 hours, that'd be 450 miles, but they went slower. I don't know. Take that back. Let's see here. They went 50 miles an hour for 9 hours. I'm thinking of time here. 50 divided by 9. What's that, about 4.5, 5? I don't know. Somewhere less than how far apart? 40, they're going 40 miles an hour back. I don't know, somewhere less than, let's say, 1,000 miles. Again, just ballparking it. Okay, step 2, no picture's going to help us here. I'm going to put step 3 right over here, just to save a little bit of time and space. So step 3, we're going to let this equal number of miles. That's our distance. We'll call that D. D is the number of miles between Asheville and Chapel Hill. Okay, step 4. Okay, it's a distance equals rate times time problem. So our situation 1 is we're going to Chapel Hill. And our situation 2 is we're going back from Chapel Hill to Asheville. So to Asheville. All right. I make my chart. Okay, distance. Looks like my distance is going to be in miles because I'm doing 50 miles per hour. Equals rate. And the rate is in miles per hour. Times time. And which says 9 hours. So this is obviously in hours. Okay, let's see. So what do we know? We know the distance. Okay, so we're looking for the distance between Asheville and Chapel Hill. We're calling that D. So going to Chapel Hill is D. Going to Asheville is also D. So the two distances are equivalent. Okay, we know our rate. On the way to Chapel Hill, they averaged 50 miles an hour. So this is 50. And on the return trip, they averaged 40 miles an hour. So this is 40. Now, I don't want to introduce another variable. So here's where I want to recognize that when I say distance equals rate times time, that time equals distance over rate. So the time is going to be 50 over D going to Chapel Hill, and the time going back to Asheville is going to be 40 over D. Again, I'm not introducing another variable, otherwise I got to come up with other equations. Okay, and what else do I know? Well, I know the total time is 9 hours. Okay, so step 4, I know total time equals 9 hours, which equals time to Chapel Hill plus time back to Asheville. Okay, well that's going to help me get my equation. So this comes up with, so 9 equals, the time to Chapel Hill is right here, 50 over D, plus the time to Asheville is 40 over D. And there's the most difficult step, step 4, kind of putting it all together and coming up with an equation. Okay, now let's do our solving. Okay, so this one shouldn't be too bad because we know about, whoops, I think I made a mistake here. Distance over, I did. Hope you caught my mistake. I made a mistake right here. Looking at my notes and realizing I made a mistake. Okay, so there we go, another mistake your teacher made. Okay, time equals distance over rate. So D over 50. I got that backwards. And then D over 40. Sorry about that. Let's come down here and let's change this. Okay, so this is D over 50, time to Chapel Hill. And this is D over 40. I bet you caught that before I did. Good for you. Okay, so step 5. Let's solve our equation. Okay, I've got 9 equals D over 50 plus D over 40. Okay, my lowest common multiple of the denominators is, well, this is a 1, this is a 50, this is a 40. Turns out to be 2,000. So I'll multiply both sides, everything on both sides by 2,000, because I don't like working with fractions. Left side is 18,000, I hope. Right side is 40D plus 50D. That's much nicer. Let's combine like terms on the right side. So 18,000 equals 90D. Divide by 90. Divide by 90. And D is equal to 200. Okay? D is equal to 200. So that tells me we have 200 miles. D is equal to 200 miles. Okay, between Asheville and Chapel Hill. You'll notice I just did kind of a quick, if I go back up to here, I did kind of my thousands pretty high, but I'm certainly less than 1,000 miles between those two. Okay, so now let's do a quick check here. Okay, so step 6. I can get my check on the paper. Oh, yep, there we go. Okay, so let's see. We know that our total time is 9 hours. Well, 200 miles at 50 miles per hour, that's going to Chapel Hill. Well, that's going to be 4 hours. 200 divided by 50. And then, of course, 200 miles at 40 miles an hour, well, that's going to be 5 hours. So there is your total of 9 hours we were looking for. Okay, one more example. A little bit different. Okay, so example 3. Exactly 1 hour after the Gallavans head north on I-77, the Laughlin's set out from the same point to catch them. The Gallavans travel at 50 miles an hour, so there's a rate, while the Laughlin's are traveling at 60 miles an hour, so they're going to catch them. How long does it take the Laughlin's to catch up with the Gallavans? Okay, so step 1. Identify what we're looking for and use units and be clear. Number of hours. The Laughlin's are traveling. Because that's when they're going to catch up. They're going to catch up in the time it takes them to travel. So step 1, we're looking at the number of hours the Laughlin's are traveling. Okay, we of course know that because we have a constant rate, and we're trying to catch them, so we've got a distance. We know this is distance equals rate times time. And let's ballpark this. I don't know. 60 miles an hour, you got to catch up. You get 10 miles each time. I don't know, less than 10 hours. I'm gonna ballpark less than 10 hours. After 10 hours, they will have gone 600 miles. After 10 hours, they will have gone 500 miles, so they'll have caught up by then. They'll have traveled 100 miles further. So I've overshot it here, but I'm looking for an answer that's fewer than 10 hours. Okay, again, not much help for a picture here, so let's go to step 3. And again, I'll put step 3 right here, simply to save some paper space. Okay, and the number of hours the Laughlin's are traveling, well, I'll call that T. That's time. Okay, step 4, the hard step. Okay, so in this case, we got 2 families traveling. So we've got the Gallavans and the Laughlin's. Okay, let's do our chart. Distance. And what's our distance? We're talking about 60 miles per hour, so our distance, again, looks like all my problems to do miles and hours. Distance equals rate. And our rate, again, is in miles per hour. And that means our time, which we're looking for here, we've already indicated with hours. Our time is in hours. Okay. Number of hours the Laughlin's are traveling is T. Okay? We got rate. Gallavans are at 50. Laughlin's are at 60. which means I have the distance for the Laughlins, and that's 60 times t. Well, the Gallavans, if the Laughlins are traveling for t hours, the Gallavans left 1 hour prior to that. So the Gallavans will have traveled for an additional hour. They left earlier, so their time will be an hour longer than the Laughlins. So their time is t plus 1. And I'd argue this is probably the hardest piece right there. If the Laughlins traveled for t hours, the Gallavans left an hour earlier, so they will have been traveling for an hour longer, an additional hour. And this will help me now, because now I have 50 times rate times time, and so you have t plus 1 here. Okay, so now what do I know? I know the distance they each travel is the same. Okay, let's see here. Distance Gallavans travel equals distance Laughlins travel. Okay, I know that because they're going to catch up. The distance is the same. Well, the distance the Gallavans travel I've defined right here. So 50 times t plus 1. The distance the Laughlins travel I've defined here on my chart. This is 60t. And there you go, I have an equation. All right, that looks good. I have an equation, now I'm in a good place. Let's go ahead and solve this equation. That's step 5. Again, step 4 is the hard one. Takes the most practice. Okay, so let's see here. I have 50t plus 50. I'm going to go ahead and multiply and distribute the 50. And that's equal to 60t. I'm going to bring my t's to the right, so I'll subtract 50t from both sides, and I have 50 equals 10t. I want to solve for t, so I'll divide by 10, and I have t is equal to 5. So, let's come down a touch here. I think I've got it. So the number of hours the Laughlins are traveling is 5 hours. Okay, so t equals 5 hours for Laughlins to catch up. Okay, let's do a quick check on this one, or step 6. Let's see if it makes sense. You remember I said 10 is my. I knew that 10 was too high, so 5 is a ballpark. Looks like a pretty good answer. Okay, let's see here. So, in 5 hours, that's how long the Laughlins are traveling. In 5 hours, okay, the Laughlins travel. My handwriting is getting sloppy. Sorry about that. Because the Laughlins are traveling, let me come up my chart here. The Laughlins are traveling at 60 miles per hour. So they're going to go 60 miles times 5. They're going to go 300 miles. Okay, they went in 5 hours. Well, the Gallavans, if the Laughlins travel for 5 hours, the Gallavans travel for 6 hours. Remember, they left an hour earlier. So in 6 hours, Gallavans travel. They were going slower, so they're doing 50 miles an hour times 6 hours. And look at that, they also travel 300 miles, so that means they caught up. Okay, these problems take practice, no doubt about it, but it makes a huge difference in your step 4 right here. Okay, to create this table, be very clear with your unknown, try to keep it down to one unknown, and build from the information you have in the problem to come up with your equation.